databases so that you can speed up certain queries. In fact, let me go ahead and show you in my VS Code environment with this same database how long it takes to execute a representative command. I'm going to go ahead and do timer.timer on, which is a SQL-like command that's just going to count how many seconds or milliseconds it takes to run each and every one of my commands, just so I can see it without having to look at my watch and time it manually. I'm going to now do something simple like select star from shows where the title of the show equals quote unquote The Office. So I'm just curious to know how many seconds or milliseconds does this here command take. Enter. And it's pretty fast. In real time, it took definitely less than 1 second. In real time, it took 0.043 seconds. So that's actually pretty darn fast. But I bet I can speed it up even faster. Let me propose to do this. Let me build my own index inside of the database's memory using syntax like this. Create index, and then the name of the index, on the name of a table, these columns specifically. In other words, if I'm the designer of this database, and I know that my users are going to be searching on the names, the titles of TV shows quite a bit, I can in advance tell the database to build a fancy tree-like structure in its memory, or RAM, so as to speed up searches for values therein. So how do I do this? Well, let me go back to VS Code and let me simply do create index. I can call it anything I want, but I'll just be clear with title underscore index so I know what I'm indexing. What table do I want to create this index on? Well, the shows table, specifically the title column therein. So here I have specified create an index, so a fancy tree-like structure in memory on the shows table's title column. Enter. So that itself took a decent amount of time, almost half a second, but that's a command I'm only going to run once. So it's an upfront cost, but hereafter I can amortize that cost over many more selects. Let me go back up into my history. This was the exact same query we executed a moment ago, which previously took 0.043 seconds, but this time, after creating the index, 0.001 seconds. And you might have thought earlier 0.43 was already pretty darn fast. I mean, 0.001 is an order of magnitude faster. What's the implication of this? Well, one, the human users of your website or application are going to get answers much more quickly. And maybe more importantly, in the real world, if I can handle if this query is like 1/40th the speed of the previous query, I can buy 40 times fewer servers to handle my users, because presumably a database server in the real world can only handle so many users at once. So if you speed up your query by a factor of 40, you can get away with that many fewer servers and that much less money as a result. So building this index in memory can be super efficient with the result in time. Now, what's the trade-off? Well, as in every discussion of efficiency thus far in design, there's going to be a trade-off. And when you build one of these trees in memory, typically known as a B tree, which is not a binary tree, it's literally a B tree, it's essentially a tree that's very short, or as short as possible. So it's not a binary tree in that each node has only 2 children. It might have 3 or more children as well. And the idea of having lots of children in this tree is that it kind of pulls the height of the tree up. So it might be very wide, but it's very short. So the amount of time it takes to get from the root node at the top to any leaf node at the bottom tends to be fairly minimalist. And you don't have to do any of this. There's no pointers. There's no C code. You, the developer, don't have to do any of this. When you create an index, what's happening underneath the hood is that kind of structure is being created for you instead. And we can really see this maybe with one of our same queries from earlier. Let me go ahead and propose that in VS Code, I bring back one of our slower queries from before. Even if you're not 100% comfortable with the syntax, just take on faith that it's the same fairly slow query I executed a bit ago. Select the title from the shows table, the stars table, and the people table, where the shows table's ID equals stars.showID, and people ID equals stars.person ID, and the name equals Steve Carell. I'm going to go ahead and hit enter, and because I've turned the timer on, we will now know mathematically how long this earlier query takes. Thinking. All right, and here we have 3.483 seconds. Like, that's annoyingly long, if you will. Like, that's going to be an annoying website waiting and waiting for the response to come back. And it's certainly going to cost other people time, because if I've got multiple users on the website, they too might be wanting to execute queries as well. Just to show how impactful these indexes can be, let me go ahead and revisit a query from earlier and show that we can speed up even our more sophisticated queries as well. Recall that when we were searching for all of Steve Carell's shows earlier, we did this. Select title from shows where the ID of the show is in the following subquery. Select show ID from the stars table where the person ID equals this subquery. Select ID from people where name equals Steve Carell. Close parenthesis, semicolon. I have my timer on now, though, so we'll see how long this one actually takes. Enter. And it's not too slow, but 0.215 seconds in real time. OK, can we do better? Well, notice in this query, we searched on a couple of columns. One, I searched for Steve Carell on the name column in the people table. And I also searched for the person ID column in the stars table. In other words, when I was asking SQL to filter my results by those two where clauses, person ID and name, it was probably doing a lot of work. And you can think back now to week 3 of CS50 and even week 0 of CS50 when we first implemented linear search, searching the phone book page at a time or searching the lockers one at a time. Linear search was slow. But these SQL tables are really just really tall lists of values. So if you want to search for a person ID or you want to search for a name, if you do not have a fancy data structure in memory already, like one of these so-called B trees that an index gives you, what is the database going to do? It's going to literally search over every person ID and every name looking for the values you care about. So can we help the database out? If I know I am frequently going to search on person IDs and names, let's create 2 indexes. So let me go back to my SQLite prompt and create one index called, say, name index on the people tables name column, because I want to search for names like Steve Carell. Semicolon, enter. It's thinking. That took over a second, but it's a one-time operation. Let's create one more index called, say, person index on the stars table's person ID. That too is going to take a moment, 2 seconds, but it's a one-time operation. Now, let's rerun my earlier query, remembering that previously it took 0.215 seconds. And that earlier query was, as before, select title from shows where the ID of the show is in the following subquery. Select show ID from stars where person ID equals the following subquery. Select ID from people where name equals quote-unquote Steve Carell. Close quote, close parenthesis, semicolon. Previously, again, this query took 0.215 seconds, but gave me all the results I cared about. Now when I hit enter, it's instant, 0.001 seconds. So hundreds of times faster than the previous query just by building up these indexes in memory. So at the end of the day, what's helpful about these indexes is the massive improvement potentially in speed. But if we looked at how much space this database is taking up on the system, it's probably going to be more space because we have to store these B trees somewhere in memory or on the server's hard drive. And it turns out, because we've created these indexes, if I go about inserting, updating, deleting data over time, I'm actually going to slow down those operations just a little bit. Not by a huge amount, but presumably the database has got to keep this tree balanced, as we've discussed in the past too, so that if we insert or update or delete things, we make sure that the tree itself is still efficiently stored in memory. So even though we might get massive savings with our select queries, we might increase the time required for some of our other operations, but odds are if you are a very read-heavy site or application, like IMDb itself probably is, where many more people are using the data than are changing the data, odds are that's going to be a net positive. All right. With that said, enough about design. Let's focus lastly on how we might use these databases and some of the problems we might run into. Now, it turns out it's actually very common in the real world to use multiple programming languages together. Thus far today, I've been focusing really just on SQL in isolation and on Python in isolation. But sometimes it turns out it would be very compelling to write a Python program that maybe takes user input, but still harnesses the power and the capabilities of SQL by using using SQL inside of Python. And so we can actually do this by using CS50's own library, which in addition to getInt and other such functions that we implemented for you in both C and Python, in the Python library, we also have support for SQL databases. And these aren't so much training wheels as they are just very user-friendly features on top of proper SQL databases. That is to say, it turns out that when you use a third-party library to query a SQL database, there's lots of functions that you might have to pick up in this language or that. In CS50's library, we do simplify it a little bit, but without hiding any of the underlying functionality from you. And so, in fact, at this URL here, if curious, you can see the documentation ultimately for CS50's own library. But within this library, do we have functionality like that allowing us to execute SQL inside of Python? So let's do that. Let's go back to VS Code and open up favorites.py, but start from scratch here. And instead of importing the CSV package, let me go ahead and import something from CS50's own library as follows. From CS50, import SQL in all caps. This is going to give me access to SQL-specific functionality in CS50's own library. Let me then create a variable called db for short, but I could call it anything I want. Set that equal to the return value of that SQL function from CS50's library, and then specify what SQLite file I want to open. The syntax for this is a little weird, but inside of quotes, what I do is pass in a string here that says follows: SQLite : favorites.db. So it kind of looks like a URL, but there's a third slash in there. It follows a similar format overall, though. That will take care of now opening that .db file in Python code instead of having to manually run SQLite 3 as I have in the past. Now let's go ahead and ask the human for their favorite language, for instance, by creating a variable called favorite, set it equal to the return value of the input function in Python, which is like getString, and just prompts the user for their favorite. Let me now call db.execute, which is a function or method that's inside now of that database variable because of how the CS50 library opened that file, and execute a line of SQL from within my own Python code. In particular, let me select how many people like a particular language based on the CSV, which is now in our .db file. Select count star as n from favorites where language equals question mark close quote. And in this case here, not to throw too many wildcard characters at us today, but in the context of CS50's library and in the context of a lot of SQL libraries in the real world, a single question mark without any quotes around it is also meant to be a placeholder for a value like the string that the human typed in. We don't want to use F strings. We don't want to use the curly braces in this case for reasons we'll come back to. But the question mark is a placeholder that, much like %s in printf from C, will get plugged in with the actual favorite that the human typed in. All right. Now, I want to do something with the return value of this function. And turns out, when you use a select statement inside of this execute function, what you're going to get back is a list of 0 or more rows. So if you match a row, you get back a list of 1 row. If you match 2 rows, you get back a Python list of 2 rows. If you match nothing, you get back a list with nothing in it, of length 0 in that case. Now, if I only really care about one answer, like the first row that comes back, well, let's do exactly that. Row equals rows bracket 0. So I'm just, for the sake of discussion now, assuming that I'm going to get back at least one, and frankly, just 1 row. So let's just grab it with row equals rows bracket 0, because rows is a list, but row is now a single row. And now, what this function dbExecute does, per its own documentation, is it returns to you, yes, a list of rows, but much like the dict reader in the context of CSV files, each of the elements in that list of rows is itself going to be a dictionary. And the keys for each of those dictionaries is going to be the name of the columns from the SQL table, just like the dict reader is grabbing the column names from the CSV itself. So lastly, let's go ahead and print out the popularity of that there language. Print row, quote unquote, n, because I want to index into that one dictionary and get back the value of n, which, to be clear, was the alias that I gave to count star. Just so I don't have to keep typing count star, I can more simply and more succinctly call it n for number. Let me go ahead and open up my terminal window again, run python of favorites.py, enter, and my favorites say, I'm gonna buck the trend here, and I'm gonna say that C was my favorite, enter, what is this crazy error message that I just induced deliberately for the sake of discussion? So in this case here, it's underlining my entire query here under db.execute, and then I'm being told more specifically that there's more placeholders than values. So maybe a teachable moment indeed. I spent all that time talking about the placeholder value earlier, but what I failed to point out is how you place a value there. So it turns out that the db.execute method takes minimally one argument, the query you want to execute, but ideally one or more additional arguments for the values you want to plug into those placeholders. So what language am I searching for? Well, whatever value is in my favorite variable, which contains the string that the human just typed in a moment ago. So if I now open up my terminal window and pretend that never happened by clearing my screen, let me now run Python of favorites.py again, really crossing my fingers. That was the problem. Didn't do that last time. Enter. I'm asked for my favorite. I'll type in C again. Enter. And there is, thankfully, that 59. So granted, it's still a decent number of lines of code, but notice what's not in here. There's no more loop. There's no more dictionary reader. There's no more conditionals. I have used SQL instead to just declare what question I want an answer to, and I get it back in the form of some Python variables, rows being a list and containing one or more dictionaries in this case. So hopefully that sort of demonstrates how we might combine these two languages. And indeed, in the problem sets to come, we're going to do quite a bit of this. But in our final moments together, feels worth dwelling on some of the bad things that can happen in the world of SQL, much like we saw bad things in the world of C and really any programming language as well. So it turns out that in the world of SQL, and really programming in general, you can be vulnerable to something called race conditions. And the story that was once told to me was this. If you're in college, for instance, and have one roommate, and between the two of you, you've got one of those little refrigerators in your dormitory, and both of you really like something like milk. And so you're determined to make sure you always have milk in the fridge. Well, how might you go about solving this problem if one day you come home and you realize you're out of milk? You open the refrigerator, you see nothing in there, you close the refrigerator, and then you go off to the store, ideally picking up a gallon of this here milk. All right, well, meanwhile, suppose in the story that your roommate comes home, opens the fridge, similarly loves milk and realizes, oh, we're out of milk, and so closes the fridge, goes out, and tries shopping for another jug of milk. Well, what happens, unfortunately, if both of you have inspected the state of your refrigerator and made a decision based on the value therein, well, at some point, both of you are going to get home. You're going to end up with 2 jugs of milk, which is way too much milk because you don't really like milk that much, but that, therefore, is a problem. So how could we have solved this here problem? Questionable whether these props were compelling for this example in retrospect, but more for us later. The problem at hand was that both of you in the story made a decision based on the value of some variable, but you didn't signal to the other person that you're in the process of updating the value of that variable. Better would have been in this story for the first of you to lock the refrigerator physically, or at least put a note on the refrigerator saying something like "gone for milk," to prevent the variable from being updated in duplicate, if you will, at the same moment of time. Now, as silly and as contrived as that story is, it turns out it's representative of something that can happen quite a bit in the real world. Consider any popular social media application nowadays, or particularly popular posts. This photo here is, as of this morning, still the most popular post ever on Instagram based on the number of likes that it got, upwards of millions. But this is actually a hard problem for a company like Meta and any of these social media platforms to keep track of, because presumably when something goes viral online and lots of people are clicking like, there's a lot of potential changes to a database somewhere all at once, because so many people are trying to like that post at a time. And just for the sake of discussion, let me hypothesize that Meta, the company behind Instagram, maybe is using, Cs50's library for this, but more specifically using Python and SQL together, but it's really the SQL that's germane for our discussion here. Let me step out of the way here and note that in these lines of code, I'm supposing that first, a company like Meta is executing a SQL statement like this: select the number of likes from the posts table, where the ID of the post is question mark, where question mark represents whatever the unique identifier is for this here post. So that's how that's how Meta is trying to figure out how many likes does the post currently get. Why are they trying to do that? Well, if we go back to the code here, they're then getting from the first row they get back, from the likes column the current number of likes for that post. Why? Because the goal is to increment it simply by 1. So the third and final line of code here says update the posts table, set the likes value to this placeholder, where the ID equals this placeholder. And as before, I have not, unlike before, I have not one but two placeholders here, plugging in likes plus 1, so the value of the variable that we just inspected, and then the ID of the post. So where is the problem here? Well, a company like Meta and any of these social media platforms has so many servers, so many users, probably so many databases that odds are these inputs are going to be coming in at once. And much like our refrigerator example, odds are, unless Meta is smart about this, they might potentially figure out on line 1 what the current number of likes is. On line 3, actually update that to be the number plus 1. But what if some other user's like came into the database while these 3 lines of code were executing? You can imagine if things are happening so quickly, maybe the first line of code gets executed for me, and then the first line of code get executed for you, and the queries in the system essentially get interwoven somehow, such that now, even though 2 people might have clicked on like, they might have happened so quickly together that just as the first one is in the process of updating current number plus 1, the other one is in the process of updating current number plus 1, when really the math should have been current number plus 2. And they both end up writing the same value instead of one that is ultimately 2 likes higher than it once was. In other words, if you have code being executed that can somehow get interrupted by other code being executed on another server, maybe with the same database, something called a race condition can happen, much like both of us inspecting the state of the milk in the refrigerator while someone else was in the process of updating it as well. So it turns out, with a wave of the hand, there are features and solutions in the world of SQL to prevent this, and they are called transactions. A transaction allows you to say to the database, execute all of these queries or none of them. But it has to be all or nothing. It is not acceptable for part of them to get executed, but not the others. You can effectively, therefore, lock someone out of the database, though it's a little fancier than that. But it's similar in spirit to putting a lock on the fridge or a note on the fridge to signal, do not make any changes to this database until my queries are entirely done, rather than only partially done. So here then in green is the right way to do something like this for at least Meta. You first begin a transaction, then you do whatever database logic you want, ideally not much because you want to keep it quick and simple, but then at the end of your code, you commit all of those changes. So this is sort of like making change, but only saving the results to the database at the very end, so it's either saved or it's not saved. You don't get interrupted partway through. Now, besides these race conditions, there's another problem in the world of databases that can strike you as well, known as SQL injection attacks. And this is actually germane to what people have been calling prompt injection attacks nowadays in the world of AI, where people are trying to trick AI into misbehaving in certain ways by injecting inputs into them that they weren't expected. Same idea with SQL injection attacks. And in fact, these came long before prompt injection attacks historically. With a SQL injection attack, imagine taking user input via anything, via something like favorites.py, or maybe something web-based. So for instance, when Yale students log in to their website, they log in here using their net ID and password. When Harvard students do the same, they log in using something called Harvard Key. In both cases, there are form fields in the application or website prompting for user input. But here's the catch. What Harvard in this case is expecting me and anyone to do is log in with their email address and their password. But what if I maliciously and very cleverly use some funky characters or punctuation in my email address that are not valid email characters, but they are valid SQL characters. And we haven't talked much about these, but single quotes are certainly valid syntax in SQL. We've seen those. It turns out that dash dash, 2 hyphens, are also popular as well. But unlike Python and unlike C, which use other symbols, dash dash in SQL denotes the start of a comment. So in SQL, if you do dash dash anything, the anything will be ignored thereafter. So notice what I've done here is I've written my email address, mailin@harvard.edu, single quote, dash dash. Now let's see why this is germane. So here, let me hypothesize, I'll take myself out of the picture, is how Harvard might be implementing login to this database. They have a query in their Python code that says select star from users where username equals this placeholder and password equals this other placeholder. And for the sake of discussion, assume that username and password somehow in Python came from those two text boxes, the username and the password field. And then what Harvard does is check if I get any number of rows back, that means that I found a row with that username and that password. Therefore, let's proceed to log the user into the website or application. All right, all fairly reasonable, but what could go wrong? Well, here is in green the query we want to execute, but let's plug in those potential values from my own form. If I were to type in mailin@harvard.edu, single quote, dash dash, notice what happens here. And if I'm using not the placeholders, but literally format strings, F strings in Python. So the point here will be use the placeholders, use the question marks, because what far too many people in the real world do is they don't use a library like CS50s. They don't use something that solves this here problem. Here is an F string or format string in Python that formats the same string. Select star from users where username equals quote unquote something and password equals quote unquote something. This is why we don't use format strings for SQL, because this demonstrates a SQL injection attack. Notice that whoever wrote this code, at Harvard presumably, put single quotes around the username placeholder and single quotes around the password placeholder. But what if I, a malicious student, use a single quote or an apostrophe in my own email address? What happens here? Well, let's plug in mailin@harvard.edu, single quote, dash dash. Now, it's a little subtle, but notice the fact that I added a single quote at the end of mailin@harvard.edu kind of closes the first quote that the Harvard programmer wrote. And then I typed in dash dash. But recall that dash dash means ignore everything to the right. So it doesn't matter that there's another quote. It doesn't matter that there's an and. It doesn't matter that there's a mention of a password. I have essentially tricked the database into treating the dash dash and everything after it as an ignorable comment. So logically what happens really, and I'm going to gray out everything after the dash dash, the database is only being asked to select star from users where the username equals mailin@harvard.edu. Everything else is ignored. The same conditional comes thereafter. If I get back any rows, log this user in. And so the implication here is effectively that if you were to log into Harvard's system as mailin@harvard.edu, single quote, dash dash, you could presumably log in as me without even knowing my password, because you've essentially tricked the database into ignoring everything after that username. So this is a SQL injection attack in the sense that you, the user, have injected code, SQL code, into my application by just typing in user input. And so the takeaway here is that trusting user input, bad. Like, you should never trust user's input because it could be mistyped or misspelled at best, but it could be malicious input at worst. You should always assume the worst, unfortunately, of your users and somehow defend against this. So what is the solution? The right solution here, notice, and it's very subtle, would be to escape the single quote that I typed in. And we saw this earlier when I had to escape the apostrophe and hello, comma, it's me. I could, in code, make sure that no matter what the human types in, I change any single quotes to 2 single quotes to escape them accordingly. But that's going to be annoying and hard to remember all the time. So really the right solution is to do indeed what I started out preaching, which is use placeholders like question marks, which comes with CS50's library. But again, this is not a CS50 thing. It is representative of how many, if not most, SQL libraries out there let you execute SQL code inside of another language like Python. Now, a little more playfully, this is a sort of meme that's gone around on the internet here. Here's someone's car with a crazy long license plate, but with a mention of drop database table, which, as you might imagine, drop being one of the keywords we mentioned earlier, is sort of how you go about not just deleting data, but dropping all of the data in a table. And if we zoom in here, presumably what some hacker here is trying to do is trick some of those cameras that are on streets in various countries that try to read your license plate. And if someone wrote code to read license plates that trusts the user input and doesn't just allow for dash dash, but allows for drop database table, you can do really bad damage to databases by tricking them into to executing delete or drop or any number of other commands as well. And in fact, the final note that we thought we'd end on is this here, which sort of welcomes you into the world of educated computer citizens by name of someone called Little Bobby Tables. Let me take myself away for just a moment. and let everyone read here this XKCD. But henceforth, after today, if you mention little Bobby tables to most any programmer in the world with a bit of a smile, they should know who and what you are talking about. An allusion indeed to SQL injection attacks. So with all of this power, indeed as always, comes great responsibility. That then was SQL, and we'll see you next time.